So I think on Friday's class, Blumling got into a pretty good intro on what titrations are, what to expect with them. I have an example problem where we're going to do every single step along the way from the beginning to the very end once we've gone past the equivalence point. And so this kind of is any and all types of problems you might see related to titrations, at least so far, where we have like a weak base or a weak acid being titrated with a weak or with a strong acid or a strong base. You're going to get into strong acid, strong base titrations, but those are even a little bit simpler, to be honest. So this shouldn't be too bad, but it's definitely a lot of steps. And so we're going to kind of go slow up front. And then afterwards, I have some practice photos like this where these are the titration curves. So a lot of times when you're working on a titration problem, you might see a graph that looks like this. I think he even had one up on class Friday, and we're going to talk a little bit about that and then wrap it up with a Henderson-Hasselbalch equation. So let me get my paper out. But this first one up here, we have a titration where we have 35 milliliters of a weak base. Doesn't matter what it's called. All I said is weak base. And I gave you the KB of it, and then we're titrating it with 0.15 molarity hydrochloric acid. So last week, what we were doing was we were given exact amounts of both of these things. So we would go straight to a BCA table, and then we could use Henderson-Hasselbalch. Now, titrations are going to be a little bit different, where we have different amounts of that titrant that we're adding. So think about a cup or a flask sitting with that weak base in it, and we're slowly dripping in the hydrochloric acid. And so we're going to see that at different amounts. So for instance, 17 milliliters of hydrochloric acid versus, I don't know, 150 milliliters of hydrochloric acid, the pH is going to be very different depending on how much of that acid we add, which should make sense. They're reacting away. So the very first thing, and this is something that we should be able to do already, is determine the pH before we've added any acid. So at this point, all we've got is that weak base. And this goes back to certainly last exam where we were doing ice tables, where we're not even adding anything. We're not reacting anything away. All we're doing is setting up the K equilibrium constant and solving for X. And that's how we're going to get, in this case, POH, and then we can get pH. So spend a few minutes seeing if you can figure this one out. I'll go over it up here as well. But we're not doing any BCA tables yet for this first one. Is that Jack next door also doing his? That's funny. I've never been able to hear him. I didn't know he had the same time. Okay, so I haven't fully finished this one out yet, but let's go through it together. Again, all that we have in this flask is the weak base sitting in some water, or a lot of water. So much water that we don't need to worry about it in the ice table. So we're going to cancel that out. And all we're doing here is what we've been doing again for a few weeks. So KB is going to be equal to this. So, and again, we want to be using KB because we're reacting a base with water. So KB is given to us as 1.3 times 10 to the negative 10. We're going to set up our K equilibrium constant. So it's going to be X times X, so X squared over 0.255 minus X. And as some review here, what can we do to make this a lot easier, solving for x? This is a super small number, right? So we can approximate that the minus x here is insignificant. So that's the step here. We can get rid of that, and now it becomes a lot simpler to solve. So we do 1.3 times 10 to the negative 10 times the 0.255, and then take the square root of that answer. So we get x being equal to 5.76 times 10 to the minus 6. So now we're going to do what to find the POH? Negative log of that. Yep, so negative log of this, and that's going to get us, again, the POH, because that's OH minus. We want the pH, so we'll do 14 minus that at the end. So none of this is new. 5.24. So the pH ends up being 8.76. Let's take a second to pause. That should make sense because we only have a weak base, so we'd expect the pH to be a little bit basic, so above 7, and it is. Now we're going to start getting into the titration part. So yeah.
pH equals pK or pKb.
pH equals pKb. Are you talking about like with Henderson-Hasselbalch equation?
Like there's one thing when he says like pH is just like gonna be equal to pKb.
That's something different. So that's if we're doing a Henderson-Hasselbalch equation where we have some of the buffer where it's a weak acid and its conjugate base. And when he's saying the pH is equal to pKa, that's if our buffer ratio is 1 to 1, meaning, um, and I can, when I do a Henderson-Hasselbalch problem at the end, I'll talk more about this, but if we had a buffer system where we had exactly 1 mole of the weak base and 1 mole of its conjugate acid, that's a 1 to 1 ratio. We have the same amount of both parts of that buffer. In that instance, the pH equals the pKa, but that's separate from this.
Okay. So there's no conjugate acid in this equation?
Exactly. Yeah, not yet, because this is before we've done any sort of reaction. So the very first problem here is straight up determine the pH with the weak base sitting in water. We haven't reacted anything away yet. That's why I had to do this whole ice table and why we started with 0 of the conjugate acid. But now we're going to get into the part where we are dripping in some hydrochloric acid. So we are going to get some reacting now. And I'm saying we're going to add 17 milliliters of hydrochloric acid. So this is a very standard way you could see a titration problem. The first part is they want you to do it at baseline, and then they want you to start solving what's going to happen when we add this stuff in. So let's do that. And as a hint, this one, we do need to do a BCA table. Anytime we're reacting away, say like a strong acid with a weak base, we need to see how that's going to react. So spend a few minutes seeing if you can figure this one out. There's a few steps here. So as a reminder, what units do we need to use when we're doing a BCA table? Moles. Yep. So that's the first step before we do anything else. We have to go from molarity to moles, and then we can do a BCA table. All right. I'm going to start working up here through the rest of it with you guys. But again, first thing we do anytime we have a titration is we need to set up the BCA table by going from molarity units into moles. So what we're going to do is take the volume that they're telling us we're using and multiply that in liters by the molarity so we can cancel out that liter value, right? This goes back to the like train tracks of 131. And once we do that, we have values that we can use. So we have moles of our hydrochloric acid and moles of our weak base. And the reason why that's important is because we have to be, when we're talking about a reaction, we're talking about the literal quantity in moles of those things that are reacting together. Molarity is about concentration, so that's factoring in like the volume and stuff that we don't need when we're talking about a direct reaction. So then we can set up the BCA table. And instead of writing WB for weak base, all I did was write B minus. You'll sometimes see it written either way. And we know that it's reacting with those H plus hydronium ions from hydrochloric acid, and it's forming the conjugate acid BH. And we're starting with none of that. So where are we going to subtract from in this C row here? The limiting reactant, yeah. So the thing we have less of. And in this case, that's going to be the H plus. So we're always subtracting by the part that we have less of, because we know that this is going to react all the way away. And it's going to go and be added to the other side. So we have nothing of that strong acid left afterwards, and we have some of the weak base still, and we've also formed some of its conjugate acid, right? So let's do that real quick. And now this is one of the friendliest examples of these types of problems because now we can do something that is a little bit easier. Does anyone know what we can do now that we have these values? The Henderson-Hasselbalch equation. Yep. So if you've done a BCA table and you get to the A row and you still have both components of the buffer, like a little bit of both, that's when you can go straight into Henderson-Hasselbalch. We don't even need to worry about an ice table, and it's a little bit nicer. So again, somebody want to call out what that equation is? I remember. Yeah, so is that for finding Ka? Yeah, so we're going to do, so the Henderson-Hasselbalch equation is pH equals pKa plus log of the base over the acid component of our buffer. And you're right, we have Kb given to us, so we need to go to Ka. And then once we have Ka, we can do negative log of that to get pKa. So I'll do that over here real quick. So I get a Ka value of 7.69 times 10 to the minus 5. So then the pKa will be the negative log of that. So that's going to be a pKa of 4.11. Now we have everything we need over here to find the pH. So the pH is equal to 4.11 plus the log of always the base in the numerator. So that's going to be the B minus. So 0.00638 over 0.00255. Are you comfortable? Of course. And when I put that into my calculator, I get a pH of 4.51. And again, if we do a little recap, that should make some sense, right? Last time we did this, we hadn't added any acid and our pH was pretty basic. It was 8.76. Now we've started to add in some of that acid and it's dropped dramatically. Now we're at 4.51. So this is another instance of how a titration could be. It might be going simply from a BCA table into Henderson-Hasselbalch, and that's not too bad, right? We kind of already did a lot of that stuff um, earlier last week. The next one, though, we're getting into some terms that I believe were in maybe his videos or his slides. Did he talk about halfway points and equivalence points? Is that not ringing a bell for anyone? If it's not, then I'll explain it. Those are different areas that we can talk about when we're referring to one of these titration curves. And he might talk about it tomorrow. Um, but the halfway point, I gave you a little definition here too, is where half of the moles of our weak base have reacted with the strong acid. So that's it. If we have, right, we already found out the number of moles of our weak base that we have, right? It's that 0.00893 value. So to get to the halfway point, we need to react away exactly half of those starting moles. So all we have to do here is take 0.00893 and divide it by 2. Anyone want me to say that again? Do we have to redo it? Let's see. So that's a great question. So, and this one I'm also asking for something different. So the last couple we've looked for the pH, and I'll be honest, this is like one of the harder types of problems you'll see. So I don't even know if you would go this tricky on your test, but it's really good to be able to do this. So, um, instead of asking for pH, I'm asking for the volume of hydrochloric acid that we would need to add to get to the halfway point. So we're kind of almost working backwards this time. And so again, I said that halfway point is once we've gone from the starting amount of 0.00893 and half of that, let's see in our calculator real quick. It will be, yep. So half of that is 0.00465. So we're subtracting that here, and that's the amount that we have to add of our strong acid, right? So why did I put this here? Because when we are doing one of these BCA tables, the smaller amount is what we're fully reacting away, right? So if we're getting rid of half of our base, that means that whatever that half amount is, we've needed to add that many moles of hydrochloric acid to get there. Because it's going to be like the exact amount that we add here is what's getting subtracted here. Does that make sense? Because going back to where we like subtract the smaller value, if we're going to have to subtract half of this, that means we need to add that number of moles of our strong acid to react it away. It's tricky stuff, so this definitely takes some time. Um, and in this one, again, I'm only asking for the volume of hydrochloric acid that we need. So we actually don't need to go on and do Henderson-Hasselbalch or an ice table because we don't need to find pH. That would be if like he could ask you that too, go on and find pH. And we would know how to do that, right? Because we have some of both components of our buffer. We would do Henderson-Hasselbalch. And here's actually an instance where pH equals pKa. Because if we did Henderson-Hasselbalch, these two values are exactly the same. So I would be like plus log of 1, and that's nothing. So, but that's not what we're doing. What we're doing here is we need to find out how many milliliters do we need to add of hydrochloric acid so we have this many moles of it. So we need to think of what we're given in this problem. We're given a molarity and we're given a volume here. So we have this value in moles, 0.00465 moles of our strong acid. or HCl is the same thing. And we want to find a volume unit. And so what we're going to use is we're going to actually use that molarity that's given to us. So we're told it's a 0.15 molarity concentration of hydrochloric acid. If we flip that upside down, we can go from moles to liters. So that's going to look like this. Does that make sense? All I did here was take the molarity, flip it upside down so we can use it as a unit conversion. And now we can cancel out the unit of moles and find the exact volume that we had to add to get here. And for me, that equals 0.031 liters of solution. So let's say of HCl.
Why did we spread out the BCA table?
You almost, if you can do this in your head, you don't really need to. This was my way of kind of representing it as us reacting away this many moles. And this BCA table would be maybe if we were going on to find the pH, it would be very helpful there. But I think this way it makes the most sense for explaining why this is the number of moles that we had to use. Again, this stuff is tricky, takes some time. When I made this worksheet, this was probably like 4 semesters ago at this point. This was one of the active problems. Since then, he sometimes like will make titrations a little bit simpler. So I don't know if he's going to ask you to do something exactly like this on the test, but it's very fair game. So, um, but again, since you guys hadn't heard of what the halfway point is, we'll see if he ever talks about that. He might not. Next thing is the equivalence point. And this is one that I think is probably something you should know. Halfway point is a little bit more niche, but the equivalence point is that very center part of one of these titration curves. So when you look at something like this, we would call this point right here the equivalence point. And that is really like the most important thing when we're doing one of these titrations, especially if you ever do one of these in a lab. I don't think you do it in 132 lab, but the equivalence point is kind of what you're looking for. So this is going to be the hardest, probably the hardest type of problem you'll see with the titration. So I want you to find the pH of the solution at the equivalence point. And I've given you a hint to kind of explain what the equivalence point means. It's when there is an equal value in moles of your weak base and strong acid. So again, on this last one, we said that we were adding half of the amount of moles of our weak base and strong acid. This time, we're going to add the exact same amount of our strong acid. So you'll set up another BCA table, and in the B row, you're going to put 0.00893 here and 0.00893 here. And so we'll get into that. And this is one where you need to go on and do an entire ice table afterwards. This is hard stuff. I think this is probably the hardest thing you do all semester. So again, the rule we've been doing this whole time is that when you get to the C row of BCA table, you subtract by the smallest amount. In this case, it's kind of weird because they're the exact same amount. So we're going to be subtracting 0.00893 from both pieces here. And we're going to see that we're left with nothing for the weak base. And also we've used up all of the strong acid. And so the only thing we have left afterwards is that conjugate acid that we formed. And so this is a bummer This is where we cannot go straight into Henderson-Hasselbalch because the rule was we need to have something here and something here to do Henderson-Hasselbalch. So instead, what we need to do is go back to our roots of last unit and make an ice table. But to make it even more tricky, we can't go straight into the ice table with this value. Does anyone know why? Exactly. We need concentration. And so what we're going to have to do is find the total volume that we've used up until this point to get a liter value in our denominator. And this is where it gets kind of tricky and uses some of the skills that we did on that last problem. So we already know that we're using up all of our weak base, and they gave us a value for that. So we're going to use all 35 milliliters of our weak base. So I'm going to write here total volume used. We know it's going to be at least 0.035 liters, but now we need to also add in the volume that was the strong acid. And based on how we did that last problem, does anyone have a guess of how we might do this? So on that last one, what did we use as a unit conversion to get the volume? We used the molarity, yep, and we flipped it upside down to get a liter value. So that's exactly what we're going to have to do here. So that's going to look like this, where we have 0.00893 moles of our strong acid, that HCl. And we're going to flip the molarity upside down. It was 0.15 that's told to us in the problem. Let me scroll down, sorry. So we can cancel out moles. And let's see what that gets us. So 0.00893 divided by 0.15 is 0.0595. So about 0.060 liters. So again, this is why I'm saying these are tough problems. It takes a lot of steps. And on a test, if he gave you something like this, he would definitely break it up into a couple of questions. But we have 0.035 liters plus all of the volume of our strong acid, and that's 0.06 liters. So the total volume here is 0.095. And now we can do the ice table, right? Because we're going to have to do the concentration of BH we now have as 0.00893 moles over 0.095 liters. So that's 0.094 molarity. How did I find this part here? So that's the next step. All I'm doing now is finding the molarity. These brackets are another way of saying concentration units. And so I found the molarity here that we're going to use in the ice table by dividing the moles in our after row by that total volume that we found. Yeah.
Wait, sorry, how did you get the 0.06? Like,
Yeah, so this is where we're using our molarity of hydrochloric acid, and that's something that we only know because it's given in the problem. So they tell us that the concentration of hydrochloric acid that they're giving is 0.15 molarity. If we flip a molarity upside down, it can become like a unit conversion where we can go from moles to liters, which is what we need. So that's what I did here to get 0.06. And does it make sense why I had to add that to the 0.035? Yeah. Yep, because we know we're using 0.035 because we're fully reacting away that weak base, and we need to define how much hydrochloric acid did we add to react that away. And that's where we get this total volume, which we can use to find the molarity. And again, this is a tough problem because we're not even done yet. We need to now do an ice table. So the ice table, hopefully this is mostly review, but we're going to be using the weak acid that we've now been left with, the BH, plus water. And what are we going to form over here? If a weak acid is reacting with water, we're going to form it. First off, this thing's conjugate base, right? Yeah, so B minus and hydronium ions. which is what we're really concerned with here. And so now we're doing ice table. And we did the necessary step of going from moles to molarity because we need it to be in units of concentration. We have 0.094. Never care about water. Starting with basically nothing here and here. Minus x, plus x, plus x. 0.094 minus x, and x. And now we have a KB value. Can we use this to find x?
Okay.
We need Ka, exactly. So we need Ka. Do you want to explain how you know that?
Because I feel like a acid because of the hydrogen ion, so that's how you know.
Exactly. Yep. If you do an ice table, oh, that's cool. I didn't know I could drag it like this. If you do an ice table and you're forming hydronium ions, we're using an active, we're reacting away an acid. So that means we need to use Ka. So we use Kw to find that, right? So it's going to be 1 times 10. We maybe even already did this. Yeah. All the way back here, we found, no, on this one, we found that Ka is 7.69 times 10 to the minus 5. And that equals x squared over 0.094 minus x. And then again, what do we do here to make this a little bit simpler? Yep, we can get rid of the minus x because this is small enough.
Well, I left my book back in here.
Oh, you're good. There's 0.094. So we get an x value of 2.69 times 10 to the minus 3. And now we can finally find the pH because that's going to be equal to our hydronium ion concentration. So what are we going to do next?
Did you think the 0.94 and 10
Did I make some mistake? Um,
Wait, I got that.
okay, I must have messed up. 9 times 10 to the minus 5 times 0.094.
Well, no, I think.
I think, yeah, I did. I did. Yeah, exactly. Yeah, so we're going to do 0.094 times 0.094 on both sides. Cancel out our denominator, and then once we do this, we can take the square root of it to get rid of the exponent here. And so negative log of x is our pH. And that's 2.57. That was a really long problem. It took us like 15 minutes. So again, I don't think he would ever give you a straight up problem like this on your test and expect it to be like a one and done. But knowing the different steps is really important. So like to do a quick recap, first thing we did was determine what even is the equivalence point. And we said that the equivalence point is when we have reacted away all of the weak base by adding the exact same amount of it with our strong acid. So these two numbers are the same, is a simpler way of putting that. And when we do that, we're left with nothing here and nothing here. And we only have moles of our conjugate acid. And then to use that, we know we can't do Henderson-Hasselbalch because if we were going to do Henderson-Hasselbalch, we need both of these things. We only have this, so we have to turn it into molarity. And then that's what we did here. So we found that 0.035 liters is all that we used of this guy here. And we needed to find how many liters we added of hydrochloric acid. That's what I did this step up here for by flipping the molarity as a unit conversion. We found the total volume to be 0.095, did this moles divided by liters to get a molarity, and then we could do an ice table. And everything down here is kind of review. That's a lot. So if you have any questions, let me know. The next one is friendlier. And this is like the last type of titration problem we're going to do today. This is where you've gone past the equivalence point. So we've added an excess of strong acid, and we're going to see that this one is the easiest of all of them. So still spend a few minutes solving this one by doing a BCA table, but then once you've finished the A row of the BCA table, I'll explain what the next step is. Okay, let me zoom in a bit. So we set up the BCA table the same way we've done all of these so far. And when you multiply the 0.15 liters of hydrochloric acid by its molarity, 0.15 molarity, we get 0.0225 moles of it. Is that step okay for you? So this is all that I did here was what we always do with a BCA table where we go from molarity to moles. And so molarity is 0.15. We're adding 150 milliliters of it. So that's going to be 0.015 liters times the 0.015 molarity to cancel out our liters. And we're left with 0.0225 moles of H plus. This is the smaller number. So it's 0.00 versus 0.0. Yeah. So it's a great point though. So this is the first time so far where we've subtracted this number and we've been left with some strong acid still. So we have an excess of strong acid is another way of putting that. And when we have an instance like this, I'm going to say, I wrote this in the red as well. We don't even care about this guy over here. This is a weak acid. It's not going to have an effect on the overall pH because we know that this right here is from strong acid. And if we have strong acid, that's way more important than this over here, this weak acid. So we can take this mole value, and if we turn it to molarity, we have the concentration of hydronium ions, right? From there, all we have to do is negative log. So we need to do the thing again where we find the total volume used. So we said it was 0.0225 moles of H plus times, or actually we don't need to do this. We're told the volume it was. It's 150 milliliters. So we've used 150 milliliters of HCl. So we can do 0.01357 moles. And the total volume now is going to be this 150 milliliter plus the 35 mils of the weak base that we've now reacted away. Is that okay with everyone? So it's going to be 0.150 plus 0.035 liters in the denominator. So I get a molarity of our H plus as 0.073. And again, anytime you have the concentration of H plus, that's when we do negative log of it to get pH. So negative log of 0.073 is a very small number. It's 1.14. That's the pH. And again, that should make sense because we've given a ton of strong acid. We've gone to an excess of it. We've gone past that equivalence point. So now we're going to be very, very acidic, 1.14. Does this step make sense for everyone, how we found the total volume? Okay, cool. Yeah, if that was overwhelming, I'm sorry, I threw a ton of things at you guys. This is not he's going to spend a few more days talking about this. And an example problem like this big one up here is probably not the most realistic for your test, but if you spend some time, I mean, I'm recording this, you can review my work later if you want. This is definitely some good stuff to be comfortable with, and you're going to nail the other titration problems if you can do this. No. No. I think I might have even gone a bit too fast. I think what I talked about here, especially with this whole volume stuff, I don't think he even spoke about this on Friday. So I might have, that's on me. I think he might be talking about this tomorrow. So definitely don't worry about it. This is confusing. Yeah, this is I think most people say the hardest part of the entire semester. So don't worry. It takes time and practice these types of problems again and again, and you should be in a better spot. Okay. So this next one is conceptual. We're not going to do any math, and I'm going to kind of talk you guys through it. Does anyone have an idea or guess of what the pH would be at the equivalence point for titration of a strong acid and a strong base? And again, quick review, we said the equivalence point is when we've reacted away the same moles of both. Anyone have a guess? 7? Yeah, exactly. So this is the type of like true or false or conceptual problem that he might toss on for your test. It's a good thing to know. The equivalence point for a strong acid, strong base pH, or titration, sorry, is always 7. And that's because we've reacted equal amounts of both. All right, now let's talk a little bit about titration curves. I don't want to go too in depth again because I feel like I kind of threw a lot at you already. But these curves are a really good way of kind of representing what's going on in a titration. We have pH on the y-axis, and then on the x-axis is the volume of titrant added. So basically, like, how much have we dripped into this flask? And I have here a few things that I've put bars over to cover up. And I want to kind of like talk through this, see if we can conceptually understand what we're looking at here. Let's start with this red one here. So this is a titration where we're starting at pH 2. So we're starting with a strong acid sitting in that flask. And we end up at a pH here of 12. So the equivalence point in this one is going to be right there, smack dab in the middle at 7. So what do we think we're adding? What kind of titrant? Do we think it's a acid, a base? Do we think it's a strong acid, a weak base? What are we thinking here? Let's start broad. Are we adding an acid or a base here? Base, yeah. It has to be a base because we're seeing that once we have added enough, we're getting basic. So it has to be reacting away with a base. Now, do we think it's going to be a strong acid or a weak, or sorry, do we think it's going to be a strong base or a weak base? Strong. Yep. And that gets to what we talked about in this previous problem where we see that the middle of the line is right at pH 7. And also, once we've added an excess of it, we're in strong base territory. This is like 12, 13, right around the like top of the pH meter. We know we're adding base because once we've added nothing, so the very beginning of this curve, we're at pH of 2. So that means sitting in that flask before we've dripped anything in is something very acidic. And as we start dripping things in with the titration, it takes some time, but eventually we get a sharp increase. This is where we hit the equivalence point again, and it becomes basic. So it would have to react away with base. And this other one, I'll kind of say it to you guys. It's a weak acid, and we know that we're starting with a weak acid because here at the very beginning of the titration, we're at pH of like 3 or 4. So that means we're not starting all the way down here at 2. So that's how we know we're starting with a weak acid. And in this one, we're also adding a strong base. We know it's base because we're ending up getting more basic, and it levels off at the same area as the other one in basic territory.
So I identify.
Yeah.
So when would it be a weak base?
It would be a weak base if, say, we did this titration and then once it levels off, it was a little bit lower. So say it leveled off and it was around like pH of 10. That would be indicative of a weak base because we didn't get all the way up here to this high, very, very high pH territory. And some vocab that, again, I don't know if he needs you to know. Analyte is what we call the thing sitting in the flask. That's what we're looking for. And then the titrant is that thing that we're dripping in. Not sure if he cares about that, but it might be helpful if you like look up videos or something later. All right. Now I've blocked off both components of this titration curve, and I want you guys to kind of, using the same logic as that last one, tell me what you think we're starting with. So what's the analyte? And then what is the type of titrant that we're adding to it? Again, let's start with the red one. What do we think is sitting in the flask before we've added anything? So what is that analyte? Strong acid. Yep. And we know that because at the very beginning, before we've added anything, it's down at the very low pH of like pH 2. Exactly. And what is the titrant for that red line? Strong base. Yep. Again, this one, once we've leveled off after adding a lot of it, we're in the strong base territory of like pH 12.
Box where the
Strong acid, strong base. Yep. We're starting with a strong acid and we're titrating in a strong base. Now, how about the green one? What are we starting with again? Still strong acid. Yep, we know that it's at the exact same point as the other one. And what are we titrating in? Weak base. There we go. Sweet. So this one, this type of thing, titration curves, with more practice, it's like very quick. He might throw one of these on the quiz, but it's a very important thing to be able to kind of recognize what you're looking at with these. And then this last one, do we want to do it? It's a Henderson-Hasselbalch problem. Let's do the extra practice. All right. So we have here a 20 milliliter solution of 0.22 molarity C5H5NHCl. And we're adding in 14 milliliters of 0.2 molarity KOH. So KOH, what is this? What is potassium hydroxide? Strong base. Yep. So we're adding in, we could say we're titrating in strong base to this weak acid. And I know this is a weak acid. One, because they gave us a Ka, kind of starting with that. And it has an extra little proton sitting around here. And the Cl is that thing called a counter ion that's kind of balancing the H plus from that acid. So do this one. This should be review from earlier last week where we're doing Henderson-Hasselbalch with a BCA table, and that's it.
there's.
Yeah.
And then.
No.
That's what the equals is for.
Yeah.
0.
Exactly. Yep. Anyone get an answer for this one? Let's see, what did I do? Okay, I got 4.99. So let me show you my work, see if there's something that maybe you see I messed up on. But on this one, we have the weak acid reacting with that strong base that we've added, forming the weak acid's conjugate base. And again, we need to go from molarity to moles for our BCA table. So I did, again, like 0.02 liters times 0.22 molarity for this top one. And we always subtract by the smaller value again in the BCA table. So we're subtracting away 0.0028 moles, and we're adding that to the conjugate base. That's what we're forming here. And when we have, as a reminder, some leftover weak acid in its conjugate base, so we have both of the parts of the buffer, that's when we can go into Henderson-Hasselbalch. So that looks like this: pH equals negative log of the Ka to get pKa. This is pKa here. Plus log of base over acid. So this is an important step. A lot of times people mess up what goes in the numerator versus denominator. So this is the base component of our buffer. So this has to be in the numerator, and this has to be in the denominator here. And it ends up being 5.23 is the pKa plus, and then log of this value is a negative value. So it's really 5.23 minus 0.243. And that rounds to about 4.99. Yeah. Did you type this whole string out? I would be careful with that because anytime I can break up a calculator thing into multiple steps, I do to be safe. So like if I do log of 0.0028 divide 0.0016. Oh wait, I must have messed up. This should be a plus value. Did you get that?
Um,
I think I messed up here. It ends up being positive 0.243. All right, that's on me. So it should be 5.23 plus 0.243. Sorry about that. So the pH is actually 5.47. Do we feel good about this stuff though, Henderson-Hasselbalch? Sweet. All right, that's all I got. Again, sorry about throwing a crazy amount for